The consequences of improperly curing a rotationally molded part are numerous. Achieving a high-quality roto-molded part requires the molder to pay close attention to several factors. The process begins with a molding machine that has the capability to closely control molding conditions, a well-designed mold, a quality grade of resin, and the knowledge of how to determine the correct cure of a rotationally molded part. ARM publishes information supplied by resin producers to aid in choosing a product that meets your end-use requirements. Equipment manufacturers offer assistance to ensure that your needs in this area are satisfied, but the final contribution for satisfying your customers' desires is based on your decision as to whether or not the molded part has been properly cured. In this video, we will describe the basic mechanism that takes place during the heating and cooling cycles of the roto-molding process. We will show how these mechanisms affect the quality of the final part produced and provide some ideas for practical tests which you can carry out to make sure that the correct cure has been achieved. So we ask the question, how do you tell if you have obtained a good or complete cure of that molded part that you're shipping out of your plant? Let's begin by describing what we mean by correct cure. A correctly cured part may have slightly different physical characteristics depending on the resin that is being molded, but the definition remains the same in any circumstance. Correct cure is when the resin inside your mold has been processed at optimum conditions so that the final part possesses the best properties that it has to offer. It will not make an inherently weak material strong, nor will it overcome faults in the mold. Although the significance of correct cure is a factor regardless of the resin system being molded, the information provided here relates specifically to standard powdered polyethylene resin, which is the most widely used material in roto-molding. Characteristics and quality control testing as they relate to cross-link polyethylene and liquid PVC systems will differ from those described here. First, let us briefly review the molding process and what takes place as we progress through the heating and cooling cycles. The mold is charged with the proper amount of resin to give us a part having the desired wall thickness. After closing the mold, it is moved into the oven, where heating and rotation is applied to form the part. During the first few minutes of the cycle, the mold and material begin to heat up. Once the softening temperature of the resin is reached, it begins to stick to the mold surface, with the finer particles being the first deposited. Melting of the particles begins as they are deposited. This layering process by particle size continues until all of the resin has been deposited on the mold. As sintering and melting takes place, air is trapped between the individual particles of plastic. Part of the curing, fusion, process is to allow enough time to elapse and enough heat to be applied to ensure that most of these bubbles are eliminated from the wall of the molded item. At the end of the heating cycle, the mold is transferred to the cooling station. The material is still hot and molten at this point. As cooling commences, the resin begins to crystallize and solidify. Cooling continues until the molded part is sufficiently cool to be removed from the mold. So, you can see that there are all sorts of process parameters which can affect the cure. Let's look at the heating cycle in a bit more detail. Obviously, your heating needs to be sufficiently intense enough to get the temperature of the mold and resin high enough for the melting and curing, fusion process to take place. In commercial operations, you will want to minimize the oven time to keep overall production rates high. But there will always be a limit to this, as the curing process takes time to complete properly. Beyond a certain point, no amount of rapid heating will ensure correct cure. If heat is applied too rapidly, the resin next to the mold surface will be overcured, even though the material at the inside surface is undercured. Therefore, we must have the correct temperature and cycle time relationship to achieve optimum results. How, then, can we ensure that our molding conditions are correct? Monitoring systems like the roto log are now available, which track the temperature inside the mold. But if you haven't got access to this, a carefully planned program of trials will be necessary. If the material being molded is the same as or very similar to one that has been run previously, the establishment of molding conditions is fairly straightforward. Molding a new product or a new grade of material will require more extensive experimentation. In most instances, these experiments will be run at a set oven temperature, which corresponds to that being used for other molds or to maintain required production rates. This leaves time as the variable. Visual inspection of the interior of the parts molded will tell you how well each is cured. A severely undercured part is relatively easy to detect. The interior surface can be extremely rough with discrete resin particles or even loose powder still present. As the curing process continues, this surface becomes progressively smoother. But be careful. You can overcure as well as undercure a part. Parts that are overcured will have an inside surface which is very smooth and exhibit a somewhat glossy appearance. Depending on the degree of overcure, the inside surface will be discolored, looking yellow during the early stage of overcure and at later stages even brown. A very noticeable acrid smell from the interior of the molded part is another indication of overcuring. Between these two extreme conditions of undercure and overcure, there is a time frame where the part is reasonably well cured. This time frame is known as the molding window. Parts with approximately optimum cure will have a reasonably smooth interior surface and few bubbles in the wall. A good grade of rotational molding resin will have as wide a molding window as possible to give you, the molder, some flexibility in your processing. So much for simple observation. If optimum cure is going to be achieved, which is desirable, you will need to go further in your evaluation of the molded part. This means that you will have to perform some type of physical property testing on molded samples. The falling dart impact test is a useful, practical method for this purpose. If you impact test moldings that have been cured over a range of oven times and plot these results against cycle time, you will end up with a curve that looks like this. You can see that the impact strength is low in samples that are either undercured or overcured. Between these two extremes is an area where the true potential of the resin is being achieved. By examining a plot such as this, you can make a sensible decision concerning the appropriate molding conditions for your product. However, when running these tests, you must be aware of the variables that can affect the results. Most importantly, the impact test specifies that samples should be conditioned at -40 degrees before they're tested. This is very important if reliable, repeatable data is going to be obtained. Samples should be taken from the same area of the molding, as there can be significant variation in cure in different sections of the parts. Impact strength is also influenced by relatively small variations in the specimen thickness. If you don't currently have an impact test apparatus, it is strongly advised that you consider acquiring one. Complete test apparatus can be purchased ready-made, or a simple unit can be built using the instructions available through ARM. Another possible source of information for equipment required to perform this test and others that you may consider is your material supplier. Being a molder desiring to produce a quality part, you should be aware of all things that can affect the cure, and in turn affect physical properties and the molding performance of the material. As an example, where colored parts are being produced, such factors as pigment type, loading, and mixing intensity can alter the heating and cooling conditions required for optimum cure. Knowing this information, you can make adjustments in the oven time to ensure that optimum cure has been achieved. What else can you do to determine correct cure? You can look for the presence of bubbles through the cross-section of the molding. Using a sharp implement, peel a thin sliver of plastic from a cross-section of the molding. When doing this, make certain that you know which surface represents the inside of the molding and which represents the mold surface. Now, look at how the bubbles that remain are distributed through the cross-section. A small battery-powered slide viewer will help you see this clearly. It is unlikely that your molding will be completely free of bubbles, but at least the area nearest the mold surface should be substantially bubble-free. If a viewer is not available, it may help to highlight the cross-sectional surface with ink. While the ink is still wet, wipe the surface. If bubbles are present, they will stand out as dark spots. Since there is no definite criteria defining the number of bubbles that might be present when optimum cure has resulted, make an educated judgment as to what stage of cure exists in the molded part. It is known that the bubbles should be minimal and that they should only be present in the area of the cross-section representing the interior of the molding. If numerous and throughout the cross-section, it is highly unlikely that you have achieved optimum cure. Following the procedures that have been described, you should be able to optimize your oven time. But what about the cooling cycle? Although it seems that the cooling stage of the process is less critical than the heating, it too can have a significant effect on the cure and performance of the molded part. ARM sponsors ongoing research into the cooling process at Queen's University in Belfast, Ireland. Here are some guidelines relative to cooling. As cooling commences, the resin begins to crystallize and solidify. The more rapidly this occurs, important properties such as impact strength and tensile elongation improve. However, you can encounter serious warpage problems where cooling is too rapid. This is particularly true with large, flat-sided parts. Of course, rotomolders all have to live in a commercial world. In reality, heating and cooling cycles also have to be optimized to loading and unloading operations, to types of molds on an arm, and to hard economics. However, the hope is that this video has pointed the way for you to develop manufacturing practices that will help assure that you are producing quality moldings. Don't forget, correct cure means less scrap, more profit, and more satisfied customers.